And welcome, Mindsetters, to this session of Learn Extra Live. Thank you to all the people at Macmillan for sponsoring this awesome event. So, guys, I hope you're ready. You've got your pens, pads, and pens out. I said pens, phones. Yes, you have your phones out. But besides that, it's Ty and Phil here doing the show. So, Phil, how are you doing?
All right, thanks, and you, Ty.
Good, good. What are we doing today?
We're going to be taking a look at some organic reactions, and I've got a cool experiment lined up for us later.
All right, cool. So, let's actually have a look at that.
Absolutely.
So
I'm going to take my spot at the board.
All right. So, Mindsetters, you know the drill by now. You need to get on the page, chat to me, www.facebook.com/learnextra. Let me know what you guys are thinking. If you're lost in it, if you need help. That's why you guys need to post on the page, because as I keep saying, I can't read your mind through the TV. I know, it seems like under this hat I could, but I can't. So make sure you guys talk to me so we can help you guys out. And don't forget to visit our updated website, www.mindset.co.za/learn/extra/live, so you can get all our schedules and notes. But I'll be posting them on the page, so make sure you watch out for that. But for now, we have a session to do, and Phil's going to take it away. Phil, take it away.
Thank you so much, Ty. Okay, well, guys, we're going to be taking a look at organic reactions, and organic reactions is encompassing a lot of stuff. Now, a lot of people say that this is only 1/4 of your organic section, and that is not true. Organic reactions is the place that they like to ask you IUPAC naming, they like to ask you organic molecule properties, and that's stuff that we dealt with last week. So I don't want you to forget about naming and about properties. Organic reactions is where all the business is. Okay, so let's just take a look at what's coming up today. Okay, so 3 major parts. We're going to start taking a look at identifying reactions as substitution, addition, or elimination, or combustion. Okay, so there's 4 types of reactions I want you to be watching out for today. Now, a lot of you are saying there's too much to write down. Guys, you're moving too fast. Just remember that this is an hour, and this would usually take me a whole week to teach in class. So to help you guys out, Ty's going to be posting up a link to the page where you can find some notes, and I've packed those notes with all of these pieces of information. Okay, so identification of the types of reactions, that is key to this section. The next one, and this is the thing which people really battle with, and this is the prediction of the products, reactants, and conditions that are needed for each one of these reactions. Okay, so guys, please, I want you to practice identifying first. That's the first step, and I'm going to show you how. Then we're going to predict products, reactants, and all of these conditions. Now, conditions I want you to leave until last. And then the very last thing, I want to get into a past paper exam style question, and that is question 5 from the 2010 paper. So if you've got that handy, great. If you go download the notes from the website, I've actually put a link directly to those exam papers. And guys, you can download the memos, you can download the papers. Practice until your heart is content. Okay, so let's jump right into it. Let's see what these types of reactions actually mean. Okay, and these are the 4 major categories that you're going to deal with. Unless you're in first year university, everything falls underneath every one of these categories. Now, a lot of you are saying, what about all the other names that I found? Most of those you'll actually find are associated with one of these 4. So somebody the other day said, okay, what about esterification? You didn't talk about esterification. What I'm going to show you is that esterification is actually a type of substitution. What about hydrogenation? Okay, well, that's an addition reaction. If you know these 4 categories, you'll go most of the way. Don't worry about those other names right until the end. I'm going to drop their names in here very briefly and try and help you out that way. Okay, so I need you to have these 4 in mind. We're going to go through them step by step, one by one, to try to get the pattern inside your mind. Now, guys, there's a few things to look for when I'm trying to identify what type of reaction I've got. And that is how many reactants and products I've got, and the next thing is what type of reactants I've actually got. Now, you might say, okay, well, what type of reactants? There's 9 million different types of reactants here. Okay, but what I want you to focus on, is it saturated? Is it not? Is it a hydrocarbon? What type of... Now, that's the sort of thinking I want from you. I want you to say, okay, well, this one is saturated, and there's 2 of them, so this is happening. Now, this is going to make a lot more sense when I put some pictures up. I love pictures, okay, and there are a couple of pictures up here. So the first one, and this is probably the most basic one, and this is substitution. Now, substitution, just that word itself means replacement. Okay, so I am replacing something on my molecule. So there's something on my molecule which is going to be exchanged with something else. So you might say, okay, well, these blocks don't actually represent organic molecules, but they do. What I've tried to do is, using simple shapes and trying to get all the chemistry out of this, is just to talk about these shapes and how we can swap them around. So what I want you to notice is that on this left-hand part, I've got this sort of gray shape attached to a yellow one over here. And as I start to move them around, what you're going to notice is that shake-up is going to cause a change in partners. Where is the substitution going to be taking place? Now I want you to think yellow and green. On the left-hand side, they're attached to the big shapes. Now what I want you to see is on the other side, something else has happened. So what's actually happened is the green shape, the green triangle, has swapped place with the yellow. Now you might say, okay, well, Phil, I don't know what you're talking about. You're talking about shapes and colors, and it's looking kind of weird. I just want you to see the pattern. I want you to see that there's pieces on these two molecules that we started out with, my reactants, which changed places with each other. So the green shape changed place with the yellow shape. I've had to change a color in the notes, guys, so if you're following through on the notes, the colors are a little bit switched around, but you can actually see exactly the same pattern. But take a look. I've got a yellow shape changing place with a green shape. And what happens is I get two new products out. So here's the first thing I want you to look for. I've got two reactants on the left-hand side. I've got two products. That's your first clue that you might have a substitution on your hands. But I'm not always sure, and sometimes it's not exactly clear how many reactants there are because of the way that they've asked me the question. It's my number one complaint. When exams happen and people are sort of walking out of the exams, they're saying, well, they just asked it in a way that I've never seen before, and it confused me. Guys, you need to have some backup. You need to look for patterns and think in terms of this. So for reactions, I want you to see patterns. I don't want you to remember, okay, this molecule plus this molecule equals this molecule plus this molecule. Guys, there's millions, and I mean literally millions of reactions. You can't remember them all. What we're looking for is a pattern. So when I'm seeing substitution, I'm seeing parts of a molecule which will trade places with a part of a molecule on another one. Okay, so now I've got two reactants, and they make two products. Now here's the thing which usually identifies a reactant, especially in matric chemistry. Here it is. You've got saturated reactants. Now this is one of the few reactions which can happen only to saturated reactants in matric chemistry. Now, okay, so I've just noticed something here. Guys, substitution over here, you can see the correct and the incorrect spelling. Okay, just make sure that you choose the correct one. So substitution is spelled correctly on the top there, but at the bottom here, we're missing a little piece of the word there. Okay, so just make sure that if you're taking some notes, that you make that correction. Sorry about that, guys. Okay, so now what I want you to see in this, when we're doing substitution, spelled incorrectly or correctly, that I've got some saturated reactants which change into saturated products. Two reactants in, two products coming out. I want to make sure that you can identify this. So this is clue number one. Clue number two, I've got reactants going in, and two of them, and I've got my product here. Let's take a look at an example of a substitution reaction. So now the first type is probably the most simple one. So the replacement of the most common thing which is on top of a hydrocarbon, and that is hydrogen. So what I'm going to do is I'm going to choose a saturated alkane. Here it is. So I'm going to use an alkane, and I'm going to saturate it. There it is. It's on the left-hand side, and I'm going to swap one of these hydrogens with one of these chlorines. So they're going to trade places. So in order to help you out with this, what I'm going to do is I'm going to circle the hydrogen that is going to be replaced and the chlorine which is going to swap places. So what I'm going to show you now is that there's a hydrogen over there and a chlorine over there. Now what I'm going to tell you is that those two pieces are going to swap and trade places. What happens is they land up together over here as HCl. What do I leave behind? I've made a halo alkane. Now you might notice that there's something in the middle here, and this is something a little bit confusing, and that is UV light. There we go. So UV light over there, UV light is a condition. That means that this is something which I need to put in place for the reaction to happen. This means that I need UV light to get the reaction to happen. Now the UV light is involved in breaking up the chlorine, and this needs to start the reaction. So the only way that you can get an alkane to react is by using UV light and a very reactive substance like chlorine. Chlorine reacts very well with alkanes as long as you've got that UV light. Now what other types of substitution can there be? Well, let's take a look at them. So I'm going to replace now my halogen which I put on there. This is the second type of substitution which can happen. So I'm going to do a replacement of my halogen, right, on a haloalkane. Guys, now the terminology is getting thick and fast over here. So a haloalkane, there it is. It's on the left-hand side here. So a haloalkane means a halogen on an alkane. So I could have made it using this first reaction. Now, I want you to see what's going to happen in the next part. I'm going to do a substitution once again. What I'm going to circle is the two pieces which are going to swap partners. Now, chlorine is a lot easier to get off carbon because the bond is much, much weaker. What you'll find over there is that that chlorine really wants to leave. In fact, in organic chemistry, we call this a leaving group. Now, chlorine is going to get replaced by something. Now, if you take a look at the thing that it's reacting with, NaOH, just remember that sodium hydroxide has got two parts. Sodium is positive, hydroxide is negative. So the natural replacement for a chlorine is the OH. Let me repeat that again. The chlorine is naturally a negative part of a molecule because it's highly electronegative. So chlorine is a naturally negative thing. So if I replace it with another naturally negative thing, what we're going to find is that it's much, much easier for replacement or substitution to take place. Okay, so let's just circle those pieces which are going to come off together. There we go. So sodium and chlorine are going to switch partners, and there they are. Sodium chloride, good old table salt, and what the result is an alcohol. Now, this is one of the conditions which you don't really need to know, is that sodium hydroxide needs to be diluted in water for this reaction to take place. Okay, so let's just revise substitution. Substitution means the switching of something on a molecule with something on another molecule. They're going to trade places or trade partners. So in the first one, I needed UV light to get chlorine to take the place of hydrogen. So what happened was one of the chlorine took the hydrogen away from there and left another chlorine in its place. Okay, now matrix, a lot of you have started doing organic reactions already in high school, and what I want you to see is that it's very, very easy to get confused with these molecules because they actually all look the same. I want you to pay very close attention. When I do substitution, especially with an alkane and a halogen, what I want you to see is that only one halogen is placed onto our molecule. It's very easy to think that addition took place. Now, some of you are saying, okay, addition, whoa, hang on, what is that? We're going to take a look at it. We're going to see what happens next. That's going to be my next type of reaction. Now, just to finish this off, once again, trading places, this is another type of substitution which you guys need to know, is that you can replace a halogen on a haloalkane, and this is my molecule. And what I find is that it's very, very natural for another negative thing to swap its place. The hydroxide naturally takes the place of the chloride. So what I'm going to find is that chloride will run off with sodium, and they're going to be happy together, and we're going to find OH taking the place of the chlorine. So they're swapping partners. Guys, I want you to draw this out. Get involved with a little bit of color coding, a little bit of highlighting, some colored pencils. Make sure that you identify the patterns. I don't want you to memorize these reactions. That's going to be pointless. It's impossible. And it's very unlikely that your examiner is going to ask you the exact same questions. So guys, you're looking for the pattern. Okay, so next one, which I'm going to be showing you, there we go, addition. Now this is probably the simplest type of reaction that I'm going to find. Addition quite simply means the combination of two particles. So what I'm finding over here is that I've got one large organic molecule, and what happens is I find that something made up of two parts. Sometimes they're the same as each other, so it might be yellow, yellow, or green, green. Doesn't really matter. I've just used colors to illustrate that there are two parts to the thing which I add onto that original molecule. So I've got reactant number one, reactant number two, and what I'm going to find is that I've got one single product. This is a synthesis reaction for anyone remembering that term from grade 10. So I'm taking two molecules and I'm combining them together. Now here's the trick. I can just count my reactants and my products to figure out if I've got an addition taking place. Two reactants becoming one product, that actually tells me that I've got addition taking place. But now, as I said, guys, it's not always that simple. Sometimes your examiner's a little bit mean and they want to see if you really know what you're talking about. Here's the other giveaway of an addition reaction. Now, addition reactions usually and always, actually, let's just correct that, always start with some sort of unsaturated reactant. Now, what I'm going to find is that I've got an unsaturated reactant taking place in an addition. And then what I'm going to find is that my products are going to be nice and saturated. So I'm going from double and triple bonds down to single bonds. Now, before we take an ad break, what I'm going to do is I'm going to run you through the first few examples. And this one's probably the easiest to draw and the easiest to follow. Okay, now there's a very particular reason that I've drawn them the way that I have. So I've got my molecule down at the bottom here, propene, and I've decided that I'm going to do addition of hydrogen to this alkene. So I can see that there's a double bond inside my original molecule. So let's just highlight this as we go. There's my double bond. So let's just highlight the atoms which are involved. And I've decided to add to this molecule using some hydrogen. Now, I want you to follow the pattern as we go through here. I want you to see that when we go to our products, we've broken that double bond. I'm going to highlight the carbons on that side. You can see that there's no more double bond. The reason that I have to do that is because I need to make space to make new bonds. I need to go from carbon making a double bond to each other and one of those bonds opening up so it can grab onto the two hydrogens up at the top. So there's where my new bonds are going to be formed. I'm going to find that new bonds will be made between those atoms when that double bond is broken. Okay, now I'm not going to leave that drawn in because it's going to be confusing when you study this, so I just want to make sure that everyone's clear that that is where those new bonds actually form. Okay, so this is actually quite simple. To do addition, all I need is an unsaturated reactant like propene and something which can add to it, something which has got two parts, like H2. There's something else which is very special about this reaction. This reaction needs a precious metal to happen. Now, you can get away with using other metals which are slightly less expensive, but platinum is really great at doing this reaction. So when I'm trying to get hydrogen to add, one of the best ways to convince hydrogen to do anything actually is to use platinum. And this is the same catalyst that I can use in other reactions involving hydrogen. Later on, you might learn about something called the Haber process if you haven't already. This is also a place where I use hydrogen to add onto something or hydrogen to react with something. So just remember this. When you think hydrogen and you're trying to add it on, platinum is a catalyst of choice. Sometimes your textbook might tell you palladium or nickel. Don't worry about it. A very nice, reliable way to remember this. Platinum, always hydrogen. Okay, and also something else which is particularly interesting. Platinum is something which South Africa has got a lot of. In fact, we've got 75% of the world's reserves. Okay, so very, very good time to have some platinum. Right, very difficult stuff to get out of the ground at the moment. Okay, so I've got this double bond. I'm adding my hydrogen. Take a look at my product. Let's see where those hydrogens went. Those hydrogens found themselves newly bonded up to the top. I've got a saturated product, and that is an alkene. I went from propene plus hydrogen to propane. Two reactants, one product, unsaturated reactant, saturated product. This is how I tell. Now, if your examiner asks this in a style of a question, and I'm going to show you one of those, they will take away one of these and ask you to fill in the rest. Now, you've got to say, okay, well, first of all, I'm doing addition. That means that my reactant has got a double bond, and what I'm going to find is a single bond in my product. They might take away either one of these or ask you the catalyst. I want you to start thinking, how am I going to see this in an exam, and how am I going to ask this? Okay? So what's happening? I've got unsaturated becomes saturated. But guys, I think I'm going to let you absorb a little bit. What do you think, Ty?
I think so.
Take a
It's
short
been
ad
a lot
break.
of information.
Absolutely. Okay, well, let's take a short ad break, and then maybe some experiments when we come back. What do you
That'd
think?
be pretty cool. I'm going to stay here so I don't get burnt or blown up. So, mindsetters, make sure you don't disappear. Keep chatting to me on the page because I'm frantically busy right now. So make sure you keep on posting. Talk to me. Let me know if you guys have any problems or if you're lost any, if you need help. But for now, I'm going to see you after this break. And welcome back, Mindsetters. Hope you had a nice little break there. You went and did whatever you had to do. Like me, I went to get myself something to drink because I'm a bit thirsty. But yes, you are back. You're ready. You're focused with your 3Ps, pens, pads, and your phones to make sure that you're not only making notes, but you're chatting to me on the page too. So, do not forget. Also, I want to stress again, if you know anybody you think would be awesome at helping develop content for the show, please do not hesitate to tell them to email content@mindset.co.za. Please do that. But on that note, we've got some awesome experiments going on. So pay attention. Eh? All right. Phil, take it away.
Thanks so much, Ty. Okay, well, what I'm going to be showing you is called the bromine test. Some of you have been asking online, and I've decided to answer this, and this fits very nicely into our experiment, is what is a saturated compound? Okay, now I've got two chemicals over here. I'm just going to put these up here, and I think you can see the names on the front here. I've got some cyclohexene and cyclohexane. Now that means that cyclo, I've got a circle of carbons, and hex means that I've got 6 inside the ring. Now the major difference between these two molecules is that cyclohexene has got a double bond. Now a double bond means that this is unsaturated. Okay, so this compound over here that I've got in these two test tubes, this is an unsaturated compound. So for those of you wondering what it means that I've got space with those double bonds to break open to add things on. Now, for what is a saturated compound, here we go. Cyclohexane has only got single bonds between those two carbons. So what I'm going to find is that all the carbons inside these two molecules, and this smells quite strong, what I'm going to find is that all the carbons are single bonded to each other. So I've just got a few test tubes in case we need a little bit of a repeat of the experiment a little bit later on. So inside these ones, I've got my cyclohexene. Inside these two, I've got cyclohexane. Now, here's the other star of the show. What we're going to be doing is we're going to be adding some bromine water. Now, bromine is a halogen. That means that it's from group 7 or 17 on the periodic table, depending on how you look at it. But bromine is a member of the halogen family. I've got it dissolved in some water here, and you can see that bromine has got a fairly strong sort of yellowish or brownish color. Depends on how you're seeing it on the camera there, but I can actually see sort of this bright yellowish, almost brown color. Now, when I add this to these two compounds, something is going to happen, or at least I hope it will. So what we're going to find is that bromine itself can react with saturated and unsaturated compounds. So let's first take a look at what happens when I add bromine water into a saturated compound. Now, for those of you that have done properties, will notice that cyclohexane is a nonpolar compound. So bromine is also nonpolar, so what you're going to find is that bromine will actually make its way up into this. I don't need quite this much, so what I'm going to do is decant a little bit out here. So we're going to start off with a tiny bit of cyclohexane. Now into the cyclohexane, what I'm going to do is pour in some of my bromine water. And we're going to see if any of the color remains or what is actually going to happen. So observation is key here. So what we're noticing is that that bromine water maintains most of its color down at the bottom there. What I'm finding is that the bromine water keeps that sort of yellowish color down at the bottom there. I hope that you can see that against my white lab coat. I'm going to leave that down in the bottom there just for a little bit of observation. Nothing seems to be happening to the bromine water in the case of cyclohexane. That means that there's no actual reaction taking place with this bromine. I might check on it a little bit later and see if anything has happened underneath these bright studio lights, and that's a bit of a hint for you at home. Now what I'm going to do is I'm going to do exactly the same thing for the cyclohexene. So I'm going to take my bromine water, let's make sure that we've got a good dose of it, and eventually what's going to happen, and you can almost immediately see the change, is that my bromine water has discolored. It's gone from being a yellow color to being completely clear. So cyclohexene reacted very quickly with the bromine water. So just for a side-by-side comparison, let's put them next to each other. So cyclohexane didn't discolor the bromine, didn't react with the bromine. Cyclohexene reacted almost instantly, and what we find is that cyclohexene, because it is unsaturated, discolors or takes away this color of this bromine water. Bromine water itself is a good test for unsaturated compounds. If the compound is unsaturated, it means that this color will disappear very, very quickly. So for those of you going, okay, well, I've got so many words inside my head, I'm just going to repeat what I've said, and I'm actually going to draw this out on the board, and we're going to investigate what actually happened. So, into the cyclohexane, nothing happened. Saturated, no reaction. Cyclohexene was unsaturated with double bonds, and that's what unsaturated actually means. Double or triple bonds, what you can see is that the bromine water has discolored incredibly quickly. So even in this one, we can still see after some time, we've still got a very strong yellow color going on. There's nothing greatly of interest taking place, but I'm going to leave this behind because something starts to happen after a little while. So this yellow color might slowly fade as the show goes on. I'm going to come back to this in a little moment. But first, what I'm going to do is I'm going to take a walk over to my board and I'm going to explain stuff. Ty, how's the page looking?
It's packed, which is awesome for me. So mindsetters, keep on talking, keep on chatting to me. We even have a lot of people actually from Ghana. Yeah, Fishbone. He's all the way from Ghana saying, guys, this is awesome stuff. He was also looking for the notes. So I've been posting up the notes. Just scan through the other posts. You'll find some of the other note posts there. But if you do need notes, just let me know and I'll post it under your comment. But for now, we have a session to do. So Phil, take it away.
Thanks so much, Ty. Okay, well, quick change behind us. I just wanted to discuss the meaning of this word saturated to unsaturated. Okay, so now what I had was these two compounds. I had cyclohexene, which is unsaturated. And let me just highlight the part that makes this unsaturated. You can see that there's a double bond there. That double bond is ripe for the taking. That's something which something else can add to. I break this double bond to do addition. Now compare this with a saturated version. This is cyclohexane. Cyclohexane has only got single bonds between the carbons. There's nowhere for the bromine to attach to. So what I'm going to find is that unsaturated compounds will turn bromine colorless. That's a very good test for unsaturated compounds. Now, what other types of addition can we do? Well, we can do the addition of bromine, and I think we should actually complete this diagram and see what it looks like when you attach bromine onto this molecule. Okay, so cyclohexene, if I was to change this into something, if I go in and add the bromine, now let me show you the process. Okay, so what I'm going to find, and you're going to do this in steps, what I'm going to find is that bromine itself is made up of those two parts. So I've got bromine and bromine. Now these two bromine atoms are going to come and find their way onto this molecule. The question is, how did they do this? Okay, well, what I'm going to do is I'm going to slowly move these around, and first we're going to do exactly what I told you to. When there's a double bond, we're going to break it. So that double bond there is going to break. Now these bromines are going to move in, and what you're going to find is that bromine itself is going to attach itself. And we're going to find that bromine is now attached to those two carbons. Those two carbons had extra space to join on. So what I find now is that I've made a dibromo compound. Guys, if you want the name of this, we can actually write it down. I went from cyclohexene. If you want a bit of a challenge, I want you to name ahead of me, always practicing your IUPAC naming. Take a look at this. 1, 2, 3, 4, 5, 6 in my longest carbon chain. It's a circle. There are single bonds. So that means cyclo for circle, hex for 6, ane for single bonds. So this is cyclohexane, just like the other cyclohexane, except there are two bromos on here. Now those bromos are in the first and the second carbon. So this will be 1, 2 dash dibromo. So this is a really long name. So 1, 2 dash dibromo, that tells me that there's a bromo on the first and the second carbon. Dibromo, cyclo, to say that it's all in a circle, hexane. Really, really complicated name, but you've got to be able to do this. It's got one functional group and then another functional group. So 1, 2 dibromo cyclohexane. This is what we made, and this is why there was no color of the bromine left over. This is where the bromine all went to. Now, this product is no longer unsaturated. It is now fully saturated. So let me just remind you where we came from. So I'm just going to rewind, and we're going to do this slowly. Okay, so before we even named this thing, something happened. Right, we did a bit of a reaction. There we go. So we had the bromos, which came in there. We had the double bond. Now, I'm going to follow through. I'm going to show you what happened. We broke the double bond. The double bond disappeared. Now what happened was the bromine came on and joined on the bottom carbon as well, and that's where the bromine went to. The bromine color disappeared. The brown color went away. Okay, so that only happened when I had an unsaturated compound. Now let's get back to our other types of addition reactions. Okay, so let's just make sure we get through this quite quickly. I want to show you a couple of others. Now what happens if I add water? So I can do addition of water. What I'm going to do is quite quickly just highlight the parts which are adding. I can see that I can write water this way. So let's just make sure that that's correctly highlighting. There we go. So I'm adding water. Right, and water itself has got two parts, an H and an OH. Now I just want you to keep in mind that that can add either way. Now water can add onto these two, and I can see Ty's drinking his water there. This is called hydration, just as Ty's doing.
Yes, because I'm thoroughly thirsty.
Okay, and this molecule is just as thirsty. I know it's cheesy, but I'm all about chemistry cheesy jokes. Okay, all right, so this molecule is hydrating. It means that it's drinking up the water. It's adding on the water. So the double bond breaks, and I make alcohols. Now, guys, H2SO4 is your friend when you're trying to add on some water. Please don't ever put some H2SO4 on you. It's going to burn you. Okay, so now H2SO4 is the thing which I need to be able to put on water quite easily, and what I need is a little bit of high pressure to get all of this stuff together. And just think of when you're trying to pack all your stuff under your bed, you're squeezing stuff in, you need some high pressure. So this is one of the ways to remember. If you're trying to get things to go smaller, to combine into one, I need high pressure. And for H2O, I need H2SO4 as a catalyst. Now let's just see where the water went when it added. So water added over there. There we go, the H and the OH. Or it added the other way around. Okay, now the question is, which one was preferred? Now some of you might be following inside the notes and you see, okay, well I've written an extra note here. This one is the major product. That means that I make more of this than I do of the other one. Now, there's a Russian guy, Makovnikov. You don't need to know his name, but you do need to know this rule. When you do addition, the negative partner out of the two, which is the OH will want to go to a middle carbon rather than an end carbon. So let's just say that again. The OH would far rather be on a middle carbon than on an end carbon. Now I'm going to see if you can follow that same trend in the last type of addition that we're going to do. We need to get through this quickly because I want to go through an exam-style question with you guys. Okay, so there we go. HBr can add on forwards or backwards, also with high pressure. And we can see that it added forwards or backwards. I want you to see which one is going to be the major product. Now, if you've been listening carefully, you'll notice that the major product is the one right down at the bottom. The Br, which is the negative one out of the two, is going to go for the middle carbon, following Makovnikov's rule. Okay, guys, I hope that you understood addition. We're going to squeeze in a little bit of elimination before we go for a little bit of an ad break. Now, the cool thing about elimination is it's unaddition. It's the reverse. So I start out with my one saturated reactant, and I split it apart. It's the exact opposite of addition. So I can see that there are my clues. I start out with one reactant. It breaks apart into two products. I started out saturated. I became unsaturated. So I took one, I broke it into two. That is my clue. So always look for those two clues when we're trying to figure out what's going on. So let's see if we can't try and do the reverse of our addition to all of the others. And the answer is absolutely yes. Okay, so we can eliminate hydrogen. Now, I just want to warn you, this particular one is quite difficult to do. You can use platinum to put on or take off hydrogen. So when you're doing elimination, this is exactly the reverse of addition. I'm going to take two things off adjacent carbons. Now, that word adjacent means next to. So I'm going to take these two hydrogens off. Now, don't forget that if you're doing the reverse of addition, I need to restore the double bond afterwards. And there it is. There's my newly formed double bond. This is the exact opposite of addition. I take a saturated molecule and I break it apart into an unsaturated molecule and a separate piece. One reactant, two products. Saturated, unsaturated. And that's the way that I identify that I've got elimination taking place. Elimination means the losing or the subtraction from. Okay, so just two quick examples before we break for that ad. Now I want you to see on the next one, I've taken some propane 1-ol. What I can do is I can do elimination, and I think you can see what I'm going to eliminate because I can see the H and the OH over there. 2 H's, 1 O. I'm taking away water. There it is. Don't forget, restore the double bond when you're doing elimination. My saturated reactant becomes my unsaturated product. And then one very last one is that I'm going to take a concentrated base. Now, you can see that Br is definitely going to come off. That's a very good target. What else is it going to take off? Look around it. What is on the other carbons next to it? I see an H. Now, please, Matrix, a lot of you might be tempted to take an H and a Br off the same carbon. There's no ways that you're going to make a double bond that way. So make sure that the two pieces which you take off for elimination are from carbons which are next to each other. All right, so there we go. So H from the one, Br from the other. There it is in my product, and there is my double bond. Whew. I think these guys need a break. What do you think, Ty?
Yeah, because it's been a lot of information. I think that'll be a good idea.
Okay, well, I'm going to take a look at their questions online while we're in that break.
All right, awesome. So mindsetters, you heard Phil. Get your questions onto the page and let us know what you guys are thinking. If you're lost anywhere, if you need help, even if you just want to say hi. You know, we get lonely in here sometimes. But anyway, we can see you after this break. And welcome back, Mindsetters. Hope you had a nice little break there. You went and did whatever you had to do. You went to the bathroom. You went to whatever you had to do. You're back. You're paying attention. 3 P's, remember. Phone, pens, and pads, because you need to make notes while you're talking to us, but paying attention, because it's really, really important. Don't forget to keep on posting on the page. And by the way, I cannot stress enough, if you know anyone you think would be awesome at helping out the show to create content, please make sure that they email content@mindset.co.za. It's so important because we're trying to build a better network and a better supply of information for you guys. So we need your guys' help. So on that note, I've got someone who's got some more information for you guys. Phil, take it away.
As always, Ty. Okay, we're squeezing a lot in here tonight. Remember that we've only gone through 3 of the 4 types, and this is the very last type. And this is probably actually the simplest one, but it's one of the ones that matrics actually struggle with in exams because they go, I know that stuff, no problem, and they don't pay any attention to it. Okay, combustion is something reliable. It's in every exam that I've seen for the last 3 years. Guys, bear in mind that combustion is the thing which powers all industry. It's the thing which fuels the cars and taxis and buses on the roads. It fuels the power stations, okay? Right? Combustion of hydrocarbons is something which you need to know. Now, again, I'm going to start out with the pattern. Now, here's the really nice, reliable thing. I can see that combustion always starts with some sort of hydrocarbon, so I've just put it there as a gray blob. Now, here's the things that I'm going to show you. This is the most important part. My other reactant here is oxygen. Okay, now you might say, okay, well, why do I care about things burning? Guys, this is exactly the same process inside your body that's keeping you alive, that's keeping you awake, that's keeping you watching me. Your body takes in food, you breathe in oxygen. What happens? Combustion takes place inside your cells, and it's a very slow chemical process inside your cells. There's no flame, but you give off exactly the same products. I give off carbon dioxide, I give off hydrogen and oxygen, which is water. Okay, so I've got carbon dioxide and water as products. These are my signs that I've got combustion here. So my 2 reactants, one of them is oxygen. That's the giveaway, guys. I'm going to do combustion. I'm going to do oxidation with oxygen itself. So this is the original oxidation. So hydrocarbon, oxygen, products, carbon dioxide, and water. Now, a lot of you are saying, okay, well, that's really easy. That's below me. I'm not going to study that. But guys, where the problem comes in is the balancing. Please, 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 this is a thing which catches everybody. You need to be able to come up with the hydrocarbons formula, and most of you are fine with that. But here we go, the oxygen. Carbon dioxide and water come out in really weird ratios. I'm going to show you why the balancing is a challenge. I'm going to show you 1 or 2 worked examples. Then we're going to jump into that past paper question. I'm going to show you how tough it can be. Okay, so let's get into that example over there. So there we go. All right, so complete combustion of propane in oxygen. So I'm actually going to challenge you guys. I want you to work ahead of me. So propane, very quickly, propane is an alkane, follows the formula CnH2n plus 2. So there is C3H, and I want you to work ahead of me. 2 times 3 is 6, plus 2 is 8. There we go. And oxygen, guys, don't forget it's diatomic. There we go, oxygen. So I'm going to combine these two to do complete combustion. Now, a lot of you are saying, okay, well, why complete? Why do you say complete? Now, don't worry too much about this, but sometimes they're going to tell you incomplete combustion. Then one of my products is CO, or carbon monoxide. But that's very uncommon. I actually just want to worry about the thing which is most likely to be asked. And I haven't seen incomplete combustion for a very long time. So complete combustion means that I make carbon dioxide and water as products. So let's take a look at that reaction. What happens? Okay, so there we go. We've got our propane on the left-hand side. Now, there we go. So C3H8. Now, where do I get 10 oxygens from? Oh, there's so much oxygen over there, and there's so much carbon dioxide, and there's so much water. The question is, where do all these numbers actually come from? So what I'm actually tempted to do is to rub out those numbers and actually start balancing this from scratch with you. But before I do that, I just want to show you another type of combustion reaction. Now, it's not just plain hydrocarbons which can be burnt. Hydrocarbons are great if you have a lot of oil. Now, oil is something which is becoming increasingly expensive. The world is running out of oil, and people are looking for alternatives to put in their engines to power their cars, to power the buses, to power industry. And what they've found is that renewable hydrocarbon-based substances, something like ethanol, ethanol is very, very easy to produce from sugarcane, from fermenting paper waste, a whole bunch of things. You can produce ethanol quite easily. It's renewable. That's the most important thing. I can make hydrocarbons renewable in the form of alcohols. Now, here it is. I can combust ethanol in the same way with oxygen to produce carbon dioxide and water. Now, this doesn't solve the greenhouse gas problem of making carbon dioxide, but what it does do is it gives me a renewable source of fuel, and that is ethanol. Ethanol itself is renewable. If I burn it, I can make it again, and then I can burn it again. So this is a very convenient way of storing a large amount of energy. Now, just for those of you looking for terms and definitions, a hydrocarbon, which I can burn in the presence of oxygen, is sometimes called a fuel. So there we go. So when you talk about putting a fuel inside something, a fuel is something which I can burn with oxygen to get carbon dioxide and water. Now you might say, okay, well, what's the point of this reaction if I'm just burning it? I'm just going to get it out the petrol pump and burn it. What's the point? Well, the reason that I burn a fuel usually is to get energy. Now I've seen it asked in a question before, why do I burn fuels in the presence of oxygen? It's to get energy from an exothermic reaction. Now, remember grade 11, exothermic, big word. Fuels are exothermic when they burn. And that means that they can give off usable energy. Okay, into it right now. What we're going to do is we're going to go into one of those past paper questions. Now, this is question 5, November 2010. Just remember, if you're looking on the website, to look for that past paper. This is paper 2. Okay, a lot of you matrics don't know that paper 2 is chemistry, so it's paper 2, there we go, and paper 2 is our chemistry paper. Okay, now we're back to our friend. Prop-1-ene, there we go, is a flammable alkene. Flammable means that we can burn it. Okay, so we're going to jump straight into the questions. We don't have a lot of time, and I want to work you through this because this is in the notes. It says, why is prop-1-ene considered to be a dangerous compound? Okay, now very often they'll start off with a very nice and easy question like this. They say, okay, well, that's no problem. They've actually given you the answer over here. Well, one of the reasons that prop-1-ene is a dangerous compound, they actually tell you, is because the thing can catch on fire. It's flammable. Now, for anyone that lives in South Africa, and most of you guys do, you know that flammable substances in people's homes are a great problem. Paraffin, as well, is a flammable hydrocarbon, and that's an alkane. Anything which is flammable can be dangerous. You can burn things with it. Okay, but now we're going to get into the questions revolving around chemistry. Now it says, through addition reactions. There we go. There's my first clue. So addition reactions over there. It says prop-1-ene can be converted into other compounds, such as alkanes. There we go. There's my first set of products. And alcohols. Now it says, which part of the structure of an alkene allows it to undergo addition reactions? So I want you to say, okay, well, addition. Well, I've got 2 reactants, 1 product. Unsaturated, there's your clue. It's unsaturated as a reactant, it becomes saturated as a product. There we go. Which part of the structure? What we're looking for there is that C double bond C. It's a double bond between the carbons which makes this eligible or suitable to undergo addition reactions. We can make alkanes, we can make alcohols, we can go mad on this thing. Now it says, in one type of addition reaction, 1 propene or prop-1-ene can be converted into an alcohol. Now just remember what an alcohol actually is. An alcohol has got an OH on there. In one type of addition reaction, prop-1-ene can be converted into an alcohol. Now, what can we do with this? What can we say about this? How can we actually draw this out? Now, what's actually missing here is they want us to see how that happens. Now, I want to draw this out for you. How can I change prop-1-ene into an alcohol? Well, let's just draw prop-1-ene, and I want you to do this with me at home. And how can we draw this into an alcohol? Let's take a look. I've got prop-1-ene, just make sure that your drawing is right. I've got a double bond inside there. Great. Now what they want is they want us to do a type of addition reaction to convert it into an alcohol. Now, I want to make sure that people understand how I can change this into an alcohol. I need an OH on here. So the first step in doing an addition reaction, remember, is to break the double bond. So I've got my C, 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 single bond between all the carbons. So I've now made a saturated compound, and I've got an OH. Now, what was the rule when I was adding something? That something would take its place on the second carbon, not on the end carbon. Remember, I told you we need to make an alcohol, and an alcohol has an OH. Now, there's something else which needed to come with that OH, and that is an H. This also gives us a clue as to what was added. There it is. So the thing which I added in there was water. So there we go. I'm just going to draw it in the backwards position so that you can see how it added. Now this type of reaction, and they want the name of it, they want to know what this is. Well, I added water. Now anytime you treat something with water in the presence of H2SO4, this is hydration. So hydration is the addition of water, just like Ty was taking a drink of water. I take H2SO4 and I use this to help me put on the water. And that will help me answer question 5.3.2. It says, name a type of addition reaction that takes place. There it is, hydration. Write down the name or formula of the catalyst which was used in this reaction. And there it is. So let's actually put these in. So H2SO4. The type of reaction was hydration. Not too difficult when I know that there is water taking place. Now, I'd advise that you actually draw this out the first few times that you're doing this. Now it says, use molecular formulae to write down a balanced chemical equation for the complete combustion of propane. Now I've got to do a separate reaction. Now this is where people really get stuck. So I gave it to you as an example, and some of you wrote it down, but I want to see if you can do this from scratch. Okay, so propane. So it says balanced molecular formula, so C3H8. Okay, so now we're told over there, so we're trying to find out complete combustion of propane. Now some of them are saying, okay, well they talked about propene first. Why are we saying C3H8? Take a look at the name which they've written down. They've written down propane. Propane plus something equals something plus something. Now there's a lot of empty space there, grade 12s. What you need to be able to do is say, okay, well this is combustion. The first step is always identify the type of reaction. Combustion needs oxygen. My two products are CO2 and H2O. Combustion, especially if it's complete, will always result in these two products and will need oxygen. Now comes the hardest part of combustion. I need to balance this. Okay, and Matrix, what I'm going to do is tell you a little bit of a secret with balancing these reactions. Leave oxygen till last, because oxygen is present in one compound on the left and it's in two places on the right. It's very tricky to try and balance. So what I'm going to ask you to do is to balance the carbons and hydrogens first. So 3 carbons on the left. Okay. 8 hydrogens on the left. I need to have 8 on the right. Now just remember, inside H2O there's 2 hydrogen atoms. So to get 8 hydrogens on the right-hand side, I'm going to need 4 water molecules. Now here comes the problem. This is the crunch. What I'm going to show you is the problem that I have usually with oxygen. Oxygen is all over the place. Luckily, this is a nice clean example. Now, if I start to add up all my oxygens, they are everywhere. I've got how many oxygens inside carbon dioxide? Well, 3 multiplied by 2 gets me 6. So there are 6 oxygens over there. So I've got 6 oxygens over there. And how many oxygens have I got in water? 4 times 1 gets me. Okay. All right, so I've got 4 oxygens over there, 6 oxygens over there. So in total, I've got 10 oxygen atoms. Now what I'm going to see is that I've got to now place all of this onto the left-hand side, and I've got to balance this out, and that's a major, major problem. Okay, so I've got my 10 oxygens on the right. How do I get 10 oxygens over here? Well, they come in pairs, which is really, really nice for me, and that helps me balance this out. Okay, so now I think I've got a little bit of time to try and figure out what's going on here. And this gets into the last piece of question 5. It says prop-1-ene can be produced from an alcohol by an elimination reaction. They want us to use structural formulae to write a balanced chemical equation for the formation. So that means that prop-1-ene is a product from a primary alcohol. So just quickly, what we're going to do is we're going to draw that primary alcohol. And I'm actually going to leave some of this for you to do at home. So I've got my primary alcohol, which is going to make prop-1-ene. There it is. Primary means that the alcohol is on the first carbon. So the hydroxyl is on the first carbon. That is my primary alcohol. Let's see if I can squeeze in my product. There we go, my prop-1-ene. There we go. And remember that my other product of this reaction is water. Okay, so we've really, really rushed through that, but I'm hoping that people have managed to squeeze that into their brains, that this is an elimination reaction. We made the water which came off, and there it is. That was my primary alcohol. And to name the type of elimination reaction that takes place when we remove water, dehydration. And on that note, I'm a little bit dehydrated myself. I think we should just call it quits for the evening. Let them rest, absorb, read the notes.
Yes, because that's so important, guys. I've been busy posting notes on the page. Just make sure, if you're having any issues like trying to see it, just make sure you download something that can read PDFs onto your phone and you be golden. But besides that, just want to say, Mindsetters, awesome job today. You guys have been on the page, which is always a pleasure. Wait, I have a shout out to give out. Hold on, just give me a second. Yes, I would also like to thank Macmillan. Thank you so much for you guys sponsoring the show. You guys are doing an awesome job. Unfortunately, I can't find my Mindsetter, but I know we had that conversation on the page, so you know this is a shout out to you. But yes, again, thank you so much, Mindsetters. And you know what? You guys need to take care of yourselves and make sure you study hard. From me, cheers, and see you next time.